Hello everyone, I am Hanxian Huang, a PhD student working with Professor Jishen Zhao from UC San Diego. Today I'm here to present our work, Ayudante, a deep reinforcement learning approach to assist persistent memory programming, which helps to translate volatile source code into the corresponding persistent memory-aware code. This is a work achieved by Zixuan Wang, Juno Kim, Professor Swanson, Professor Jishen Zhao, and me. Here's the outline of today's presentation. Non-volatile main memory techniques combine comparable performance of DRAM and the persistence property of storage, but it also brings challenges for users on PM programming. The first challenge is PM programming either adopts PM programming interfaces, such as PMDK on the source code, or rewrites from scratch, which is non-trivial labor effort, and is also time-consuming to manually debug the new code and improve the performance. The second challenge is manually rewriting the semantics by adopting a variety of programming APIs easily leads to errors, and it requires expert experience to promise the code correctness. The third challenge is PM programming is hard because it has to promise data consistency to enable recovery across system crashes. As such, programmers are required to understand where, when, and how to use the PM library APIs to provide persistence guarantee and avoid unnecessary persistence. This leads to additional learning effort for non-experts. In order to address these challenges to assist transforming volatile source code into PM code with minimal programmer interference, we proposed Ayudante. Ayudante consists of two key components. Given a source C or C++ or Java volatile source code, it first employs a deep RL-based code generator to automatically translate the source code into corresponding PM code by inserting PM library annotations. And then Ayudante employs a code refining pipeline to parse the generated code to provide a report for programmers to further test, debug, and tune the performance. First, let me introduce the RL-based code generator. Here we identify translating a volatile memory code into PM code as a decision problem of sequential code editing. And we propose to learn the code editing policy by a deep RL model with four major elements: agent, state, action, and reward. The agent is the executor of actions on a state. A state is a pair of string and position. A string is a piece of source code, and a position is the current location in the code to take an action at. The states are preprocessed by long short-term memory autoencoder into tokens. The action is either navigating through the source code or editing the source code. Navigation actions allow the model to enumerate all possible insertion locations of PM library APIs. And the edit actions either annotate one line of code or wrap a block of source code into a pair of annotations. The reward is the feedback of an action on a certain state formulated as the sum of three penalties: step penalty, modification penalty, and code error penalty, where V1, V2, and rho are the penalty factors to control the relative importance of these three penalties. The S, M, EI are the numbers of steps, the number of modifications, and the number of errors reported by PM checkers I correspondingly. The step penalty and the modification penalty are used to encourage the RL generator to complete the PM code with fewer steps and modifications. And the code error penalty is the sum of the penalties given by different checkers to encourage the RL model to avoid the bugs detectable by the checkers in the environment. There are two phases of RL code generator model, offline training and online inference. In the offline training process, there are 4 steps. First, the policy and value network observes the new states and rewards from the environment, and then output an action. It is a 3 fully connected layer typical network. And then second, the environment applies the action to generate a new code and test it by PM checkers to calculate a reward. Here we use GCC compiler, sanity checkers, PM check and PM reorder, validation tool PM test as the PM checkers in the environment. Third, the environment returns the reward and a new code state to the agent. And fourth, the network gets the new reward and state and repeats from step 1 to output a new action. In training process, the network will optimize its parameters to learn a better action policy to insert correct library APIs and avoid bugs according to the reward function. After training offline, we got a well-trained RL generator to perform online inference. In the inference stage, the generator will directly generate the best actions and output a PM code without any model updating. Here we introduce the search strategy, multi-color tree search, with 4 steps: selection, expansion, playout, and backpropagation. Starting from the root node, it first selects the trail nodes with maximum value, and then expand the state to a valid trail node. And then in playout, evaluate the current node's position after sampling the moves to a leaf node. And finally, it uses the result from playout to update the node information from the current node back to the root node. Here we combine typical network with multi-color tree search strategy to achieve more effective and efficient search. Because the network selects potential good states by exploring the high probability node, and the multi-color tree search is kind of look-ahead search strategy that can take the future actions into consideration. Transfer learning is an effective technique which takes features learned from one domain and leverage them in a new domain with certain similarity. It can save training time and achieve higher inference accuracy in a new domain. So here we train a Java generator model by transfer learning to fully leverage the code translation knowledge learned from the C and C++ code generator. Here the H represents the hidden state of different tasks, and A represents the multi-layer perception adapter to transfer the hidden knowledge represented by hidden states from C and C++ to transfer to Java generator. Here we show an example PM code generated by our RL model. The input C code is shown in black, and the actions are marked as arrows. In this example, the agent first chooses navigation actions for step 1 and step 2, and then an edit action for step 3 to insert one annotation shown in red. And similarly, the agent performs edit action at step 7 and step 10 and generate this complete PM code. We have to mention that because of the inherent approximate nature of deep learning, it is impossible to achieve 100% accuracy for all generated programs only by a machine learning model. So we design a code refining pipeline to search for bugs that may remain in the code generated by the RL model. It consists of 3 levels. The first level is the compiler to check on the syntax and library API usage bugs. The second level is the sanity checkers, including PMDK and PM reorder, to check on the consistency and reordering bugs. The third level is the validation tool, including PM test, XF detector, and Agamotto, to perform a deep bug search in terms of crash, consistency, and failure recovery. The output of this pipeline is a code refining suggestion report for programmers to further inspect the code manually. Here we have an example output of this pipeline to report a duplicate persistence API. It identifies that the node construct already persists the tree node data, and there's no need to persist it again when calling the node construct. Here we train the RL model on volatile version PMDK example codes with the APIs discarded in the code. We test the model with the code that never seen by the model in training process and measure how well the model generates for such new code in the inference process. The testing dataset consists of volatile version source code from a microbenchmark, KV store application, and open source LeetCode solution. These programs perform similar functionality as PMDK examples on various data structures, such as B-tree, hash map, and the combination of multiple data structures. In evaluation, we first show the PM checker passing rate, or CPR, which is the percentage of the generated code that passes the PM checkers on testing sets. We use CPR to measure the generalization ability of the trained model. And here we use PMDK to test the CPR. With checkers combination of PM check, PM reorder, and PM test in the training environment, all the generated code passes checkers with the key value store workload and microbenchmark, and 78.7% parses the checker with the LeetCode solution datasets. We show 13% lines of code change on average, which indicates that the proposed framework can significantly reduce the labor efforts on PM programming. We also evaluate the performance on an Intel Optane DC PM server on list, array, queue, and the B-tree microbenchmarks. The first row subfigures shows that the generated code achieves similar bandwidth, LLC load, and data TLB load performance compared with PMDK expert code examples. Although the list data structure has a 30% higher LLC store events due to the unnecessary persistence API calls, it actually doesn't significantly affect the overall program execution performance while promising the persistency. And the second row subfigures shows the good scalability and the comparable bandwidth performance to PMDK examples by different input sizes. And in conclusion, the proposed Ayudante Framework offers efficient PM code generation with reduced bug and offers code refining reports to improve performance. And Ayudante Framework significantly reduced the burden of PM programming and shed light on machine auto programming for PM and other domains. And thank you so much for listening. Any questions are welcomed.